want to show you this work. Thank you for having me in this workshop. This is an ongoing project and I'm very interested in knowing your input since we are not expert in ambient measurement. So for us this is a very important opportunity. Thank you for having us. So let's get started with the workshop with further introduction. This is the outline of the presentation. So I'm going to start with a project overview to get you into the topic. Many of you know that many environmental project impacts of black carbon, especially on climate change. But I'm going to focus on the effect of black carbon when it deposits in snow or ice. Right? When it does, black carbon has an effect on albedo of the snow, reducing albedo, increasing light absorption, which in turn increases melting of the glacier. It's not really well known yet the net impact of this increase. It's very discussed. As you can see, there are not only a direct effect, but there are many fast and slower indirect effects that make the simulation of this effect very complex. There are large uncertainties. The most important are black carbon emissions, snow aging or metamorphism of snow, and black carbon and other aerosols optical properties, and also snow coverage. So these uncertainties limited till now the possibility to make an accurate decision on the impact of black carbon on melting of the glaciers. So we try to improve these limitations. Our interest area is in the Andes of Argentina. There are several large glaciers that we're going to try to study. We're using an atmospheric model called SICAD params, parameterized for South America especially. We're using at the moment these global inventories for emissions, and we're going to prepare this module to connect black carbon deposition in the glaciers with the climate effects that we just mentioned. We are going to base our model on these well-known models that are already implemented in regional or global climate models, right? For the sake of this talk, we're going to focus on the most advanced sub-project of our project, which is based on Cerro Tronador, or Mount Tronador, in Rio Negro, Argentina. To sum up, this is what we're going to do. We're going to model emission and transport of aerosols, estimate the position on glacier snow, and calculate the effect over its albedo and snow ice melting. This talk will be focused more in the last point, of course. I'm going to show you some experimental results and some preliminary calculations. So, for those of you who are not into glaciology, this is a fast definition of a glacier. We know that there are two important zones in the glacier. The accumulation zone, where solid precipitation, snow, is higher than in winter, is higher than the melting produced in summer, whereas at the lower part of the glacier, the melting prevails, so we lost a mass of ice, mass of water during the year. The balance between gains and loss of mass gives us the glacier mass balance of the glacier, which can be measured with several methods. For this, we are in connection with IANIGLA, the National Institute in Argentina that monitors the glaciers from Argentina. The method they chose is a combination of empirical and model. They have stakes in situ that measure the height of the glacier at different moments of the year, and they use these stakes to validate a model that includes climate data and radiation data, which allows them to get a day-by-day balance mass of the glacier, and with a very precise position resolution, which is very important, as we're going to see, because there is a large heterogeneity of the height of the glacier and the albedo of the glacier too. So what do we expect to see when we go to a glacier at the moment of the year, in April, which is the end of summer? Let's say for 2015, we can see this glacier height. We see a dark snow on the glacier. During the winter, you have snow accumulation. But after that, during the summer, next summer, you get melting of some of the snow accumulated in winter, which ends up with crust of PM-enriched snow on top of the snow, dark snow with very large concentration of particulate matter. So that's what we expect to see in April 2016 when we perform a field campaign on the glacier. This is our sampling area. This is the Tronador Mount, sorry. A close-up. And here we have the sampling points. 4 sampling points in the accumulation zone of the glacier, and 2 sampling points in the ablation zone of the glacier. Here we have a few snapshots of the sampling process. We sample surface and subsurface snow on different points, and also we have the opportunity to drill an ice core or more snow and firn core on one of the points of the glacier in the accumulation area. Here you can see the ice core and its nose core, almost 3 meters long, and all this is the accumulated snow during winter. And here you can see a dark area that corresponds to the summer of the previous year. This is the particulate matter accumulated during the melting in summer, in April 2015. And also, on top of it, there are also volcanic ashes deposited in April 2015. There was an eruption of a volcano, the Calbuco volcano, that contributed to the particulate matter on this particular glacier. Now, this is me filtering some of the samples. We collected the melted snow samples on filters for analytical chemistry. And this is the equipment we use to measure radiation on the glacier. It's equipment zone and equipment CM5 model, not model. For the clear sky conditions, we could use this aluminium support. But for the overcast conditions, we had to flip the sensor faster because the radiation fluctuated very fast. So we removed the legs of the equipment and flipped it by hand, which increased the light obstructed by the equipment, of course, as we're going to take into account in later calculations. How did we treat the results? Following recent publications, we calculated the corrected albedo this way. We corrected both upwelling radiation and downwelling radiation, mainly by the obstruction of light due to the equipment and or the observer, depending on the case, and also by the shadow projected by the equipment on the snow. In the next months, we're planning to improve these corrections using radiation calculations to know the ratio between direct diffuse and reflected light at the point we measured. And also we're going to try to verify that the cosine response of the sensor is good enough and that the absolute calibration of the sensor is accurate enough to validate model calculations about direct diffuse and reflected ratios. So,